as data block. All right. So all the transaction between main memory and cache happens, basically the unit of that transaction is your data block. So whenever you would like to bring a new block, so you'll replace the whole block and bring a new block. It's not like a fragment of the block and so on. Okay. So for example, let's say you need to bring a new block. So you will identify which block among this cache need to be evicted and then replace the whole block with a new block. Does this make sense? Okay. So based on that, so basically we also looked at the algorithm which is for a simple instructions like load. So processor issues the load request and the request goes to the cache. Then cache compares the address from which the data need to be loaded and sees whether there is a match. If there is a match, then we call it cache hit. The copy of the data from cache is returned to the processor. So basically you will execute the load. So the load essentially is saying that you go to this specific memory and read the content of that memory and load it into a particular register, right? So now when the address is generated by your ALU, so basically by adding the base offset, the address goes to the data memory. Remember your 5-stage pipeline microarchitecture. Now this data memory is nothing but our big slow memory, and between the big slow memory and the processor, we have this cache. So cache also keeps the same copy of the data which is there in the big slow memory. And now if the copy, basically what the cache has, it's what the processor is looking for, then there is a cache hit. So you can return the data from cache. If the tag does not match, that means the cache does not have the copy of the data memory which the processor is looking for. So in that case, what you have to do? You have to read the block from where the data need to be loaded from main memory. So you have to go to main memory and now fetch it from main memory. Now when you get it from main memory, you have to keep, basically you will read it from main memory, you will store a copy in the cache. Now to do that, you have to evict something from your existing cache. So basically you brought a new block which the processor is looking for, and this is your cache. So the new block has to be placed somewhere. So placing this new block in this cache means you have to evict something from the which is already there in cache. So the block which will get evicted, let's say this is the block which will get evicted. We call it as a victim block. So our replacement policy, which we discussed in the last class, will determine the new block where it will be placed, and the old block where basically the place where the new block will come, this old block has to be evicted, and this block is called victim block or victim cache. All right. Any doubt, concerns? So once we bring the new data in, then we can then serve the processor from cache with the new data, which with the data which the processor is looking for. All right. So followed by that, we looked into the different classification of caches based on block placement, block replacement. So these two things we have already seen. So I'll briefly review them, and then we will look into block identification, how we can identify a block in the cache, and basically write strategy. What happens when we need to write something in the cache or write something in the memory? Okay. So for block placement, essentially we are trying to answer this question: where can a block be placed in the cache? And we have seen that there are three strategies. Uh, if we have the flexibility to put the block anywhere in our cache, then we call it fully associative cache. So this is our fully associative cache. So in the example, we want to bring block number 12 into our cache. If we have the flexibility to put it anywhere in our cache, then we call it fully associative cache. If we have a direct mapping of this block 12 in a particular slot in our cache, then we call it direct map cache. Right. So block number 12, if it maps directly to a particular slot in my cache, then we call it direct map cache. And then they have their advantages and disadvantages. So direct map cache, remember in the algorithm, we saw that when the processor requests for a data, we need to check whether the data is available in our cache. Now, how do we do this checking? We match the tags, what the processor is requesting for, and the tags which I have in my cache. Now, in case of direct map cache, I know that if this particular block has to be there in my cache, there is only one place it can be there. Right? So I'll directly go there and check the tag at that particular block, particular slot, and whether there is a match. If not, then I know that there is a cache miss. If there is a match, then my hit time is really, really small. So every basically event will take some time. So processor request for the data. So or basically processor generates the address, and then it is going to the remember, in your memory stage, you are supposed to use this address to read the data from data memory. Now you have one cycle to get the work done, right? In our 5-stage pipeline, where is this happening? So fetch, decode, execute, memory, write back. So after execution stage, I get the address. Now in the next clock cycle, I have to take this address, go to memory, read the content, and be ready with the content, so that in the write back stage, I can write it in my register, which I'm trying to load. Now, to get this work done within the clock period, one clock cycle, so you have to figure out very quickly whether there is a cache hit or cache miss. So that's why I would like to reduce my hit time as much as possible. The time required to figure out whether the data is there in cache or not. So in case of direct map cache, this time can be really, really small, because I don't have to look for many places to figure that out. On the other hand, in case of fully associative cache, in case of fully associative cache, the block could be anywhere in my cache. So to figure out whether the data processor is requesting for is there in my cache or not, I have to look for all possible slots in the cache. And definitely this will take more time compared to what time I have encountered in case of direct map cache. So that's why this fully associative cache in terms of hit time is not a very good choice. But it has some advantages, especially when we look at replacement policy and conflict misses. So I'll come to that in a while. So in case of conflict misses, let's discuss what is conflict miss. So now let's say in our direct map cache, block number 12 maps to block 4. In the same way, because we are performing this operation to find out where our block should be mapped to. Now, there are several other blocks which also map to the same location. For example, block number 4. Block number 4 will also be mapped to the same location. Block number 20 will also be mapped to the same location. Now, let's say you wrote a program and the mapping of the data is such that you are dealing with memory block number 4, 12, and 20. So you need these 3 blocks to work with your variables. So in that case, if you have a direct map cache, what will happen? So whenever the processor requests for block number 4, you will bring block number 4 and map it into your slot number 4. And in the next moment, when you request for block number 12, you evict block 4 and bring block 12. So the moment block number 12 is requested for, what will happen? You will have a cache miss, right? Because block number 12 is not there. In that slot, block number 4 is sitting now, right? So there will be a miss. And this miss is called conflict miss. Why it is a conflict miss? Because I have only one slot and all the blocks which I need to bring in, they are basically mapped to the same slot. So I can't bring all of them at the same time. So because of that, I might have basically not so useful data in other slots. So maybe these slots are not containing that useful data for my current program. But I can't put block number 12 or block number 20 in those slots because my strategy of the way I place blocks in my cache is fixed, and it says that you have to basically put block number 4, 12, 20 in the same slot. So this is called conflict miss. Because of this conflict in the way I am mapping my blocks, because of that I am encountering misses. Every time I request for block 12 or block 20, there will be a miss and I have to bring the data. Again, let's say after accessing block 12, if I need to access block 4, then again I'll be encountering a miss and I have to bring block 4 again, right? So that's why in case of direct map cache, there is a this problem of conflict miss. Whereas in case of fully associative cache, I don't have this problem, because as long as I have a not so useful data in my cache, which I replace, I can bring new blocks and I can put them anywhere, right? So that's why it's easy to handle conflict misses in case of fully associative cache. But fully associative cache has this disadvantage of heat time being large compared to let's say direct map cache. Now, is there a better way, or is there a middle path? So the more popular block placement strategy for cache is called associative. Basically, instead of fully associative, we have limited associativity caches. So for example, in this figure, we are seeing two-way set associative cache. So the same amount of cache, we are dividing it into 4 sets, each set having 2 blocks. And now the mapping of the sets are done based on the blocks. For example, block number 4 will be mapped to block, let's say block number 12 will be mapped to 12 mod 4, so that's set 0. Now inside set 0, I have the flexibility to put it anywhere, right? So what is the advantage here? So for example, let's say I want to work with block number 12, I want to work with block number 4. Now both this block can reside in set 0 without creating this conflict miss. Now if I need let's say an additional block number 20, In that case, I have to evict one of them because block number 20 also maps to the same set. So block 4, this is 4, this is 12, 20. So all maps to the same set. So this set associative cache are the most widely used cache placement policies in practical world. You might find direct map cache in very low overhead implementation sometimes. All right. Is there any quick question before I move ahead? So the block placement in a cache is completely clear, I believe. So instead of two-way, if we have a four-way set associative cache, we should be able to figure out how to map the blocks into our cache, right? So you have to figure out like how many sets you have, and then what is the block you need to place, and then you can perform this simple block number mod number of sets to find out which set this will go to. All right, so moving ahead, we also discussed about block replacement policies because we saw that to bring new data in, new block in, we have to replace the existing blocks. So in case of direct map cache, there is no choice. You have only one mapping. So wherever that block maps to, that particular block need to be evicted, right? So whatever is there, it need to be evicted. So in case of no direct map cache, there is no choice. In associative cache, we do have this choice. For example, whether it's fully associative or let's say set associative cache, we have the choice that which block to replace. For example, let's say we have block number 4. This is block number 4. This is block number 12. Now I need to bring block number 20. So out of this 4 and 12, which one I should replace? Okay. So the policies or strategies could be, yes. These are not very stringent definitions. So cache line generally includes the address also, the tag. So basically in this discussion, what we have said that okay, address along with the all the data, we'll call it as cache line, and only the data part will call it as a block, cache block. So the strategy to replace the blocks could be as simple as random. So we just randomly select one block. And surprisingly, this is not a bad strategy. It works pretty well. Okay. Then we talked about least recently used. So as the name suggests, we will figure out which one among the different blocks which are contender to be replaced, which one is the least recently used. Okay. And based on that, we will replace it. The problem with LRU is that for every access, you need to basically update which one is the least recently used. And when your associativity increases, for example, if you have a 8-way set associative cache, then you have to keep a track out of this 8, which one is the least recently used. And this becomes, the overhead becomes quite a bit in many cases. And the benefit you get by identifying exactly which one is the least recently used is not that high. So for example, let's say you have 8-way set associative cache. So that means you have in your set, you have 8 such blocks. I think it's 8. Now the choice is that do I need to keep a track of among these 8 blocks which one is the least recently used exactly, or I try to come up with a basically subset which says that okay, these 4 blocks are among the ones which are not so frequently used by the processor. Okay, so if I can find out that okay, out of these 8, 4 are more used by the processor and these 4 are not so frequently used by the processor. If I can find out this kind of division, then I have to only figure out which block to replace to bring the new data in. And I select any of the blocks which are not so frequently used by the processor. Basically, the implementation will be much simpler and my performance will not also get degraded too much because I'm not violating the temporal locality that significantly. Because the whole idea of using or replacing least recently used is to exploit temporal locality. Now, if I have basically, let's say 8-way set associative cache, and I make sure that the uh, half of it, which is more frequently used by the processor, they are not getting replaced. I'm pretty much making sure that temporal locality or whatever I need to exploit from temporal locality, that is exploited. So that's why true implementation only feasible in case of small set of small sets like 2-way set associative cache, etc. The more practical implementations are pseudo LRU for basically 4 to 8-way set associative cache. So basically you maintain a tree structure where the basically the important ones which are not which are recently used, they are kept on the top of the tree, and the branches are the ones which are uh, not so frequently used ones. Then there is first in first out. That could be also a very valid strategy for uh, replacing the blocks. The advantage here is that uh, every block spends some time in cache because you are making sure that the block which came first, it gets evicted first. So it's a very simple strategy, but very effective one. So widely used as well. And then the more performance oriented one could be not most recently used. So you implement FIFO, but only difference here is that you make sure that if the block that need to be evicted through FIFO is the most recently used one, then you don't evict it. Yeah, just give me a moment. So what do I mean by that? Let's say these are the blocks which came in this sequence. Now I have to evict one block. So first in first out says that this block came first, so this need to be evicted. So before you do the eviction, you do a check whether this is the block which is the most recently used one by the processor. If so, you don't evict it, rather you evict block number 2. Okay, so that way you are making sure that you are not replacing the most recently used ones. Yes. Yeah, because you otherwise maintaining which block is the least recently used one becomes an overhead. When you have like large sets, 8-way set associative cache, you have to figure out which one is the least recently used, right? So every access you have to make this update that okay, currently this is the least recently used, and then after the next access you have to update it again. FIFO, so see here any block could be accessed, so there is no sequence. But FIFO, you know the sequence that okay, this block came first, this block came first. So FIFO, maintaining FIFO is very easy. Yes. Yeah. So the one which you brought first, whenever you need to remove, so you have, let's say, set of four blocks, you will figure out which of these four blocks was brought in first. That need to be removed. Rest would remain same because you need to replace one block only. Okay, so now how do we identify the blocks in cache? So the address for a cache has three parts: the tag, the index, and offset. Okay, so the block address is primarily the tag and index. So the tag value is same uh, for a set. Okay, so tag will determine. So tag is typically the more significant bits of your address. Okay, so using tag, you will identify the set. So in this example, basically it's a direct map cache. So all the blocks are in different sets. Now inside the set, how do you identify that the block you are looking for is there or not? That is done through index. So basically index is different for inside the set. The tag is same, index is different. So that's how you identify that, okay, which block, the block you are looking for, whether it's there in your cache or not. And the good part is that all these address segments, you can parallelly evaluate. For example, as soon as you get the block address, you will parallelly evaluate whether there is a tag matching as well as the index matching, right? So if tag and index matches, and then you get the block which you are looking for, you say that, okay, there is a cache hit. And then further, the offset gives you the exact data byte which you are looking for. But for bringing the data in, you don't worry about the offset part. You just get the whole block, right? Um, yeah, so the cache uses this index and offset to find potential match. And basically tag is the one which will be finally saying that there is a cache hit or not. Tag is the higher order bits of the address. So we are, in this example, we are looking at a direct map. In each cache block, there are 8 bytes, and basically the number of lines in this cache are 4 cache lines. So these are the cache lines. So this is your cache line. This is your data block, which contains 8 bytes. And yeah, you have 4 such lines in your cache. Okay. And this is a direct map cache. If we look at a two-way set associative cache, so two-way set associative cache with 8 byte blocks and 4-line cache. This is how it looks like. So you have 2 sets, set 0 and set 1. The tag for each of these sets are same, and the index value will tell you which particular block you are looking for. Okay, so this is the way you identify your cache block. Now, finally, so whatever we have discussed so far, this was loading data, right? So I am requesting for a block, processor is requesting for a block, and then you are getting the data from memory and getting basically storing it into your register. How about write? Basically store. When the processor requests for a store, what happens? So now there are two possibilities. So let's say you have a store instruction, you got the address, you are trying to store the value. So after your execute stage, you have the address. Now the address is sent to the data memory, and the value that need to be stored is also available to you. So now there could be two possibilities. There could be a cache hit. So the address where you need to write the new data, it's already there in your cache. So in case of cache hit, now you have two options. You can only update it in your cache, right? Because processor is requesting to write some data into memory. Now you have the same data copied in your cache as well as the data is there in main memory. Now you figured out that there is a cache hit. So the data, the block which need to be updated is there in your cache as well as in main memory. You can only update in your cache and don't update in your main memory. So that could be one possibility. So which we call it as write back. Okay. So we only update currently at the cache and we don't update it in main memory immediately. We wait for update for the update in main memory only when this block need to be evicted. So let's say this is my processor, this is main memory, so and this is cache. Now the CPU says that go to memory location 100 and update the value with a specific, let's say value which is, let's say 500 or 50. Okay. Now it will send this address to my cache and there is a cache hit. So I see that, okay, this particular location where I need to update the value to 50 is there in my cache. So in case of write back, what I'm saying is that I'll update in my cache, but the copy which is there in main memory, the same address is basically I have just copied from main memory. This particular location is not updated. Okay. Now when I will do this update? I'll do this update when I have to evict this block from cache. There will be a time when I need to evict this block from cache because I need to bring, let's say, new data. Then I'll decide to evict this block from cache. Now, while I evict this block, if I don't update it in main memory, then all my updates will be lost and I'll be doing something wrong, right? So the moment I need to evict this block from cache, I have to make sure before I do this eviction, I update it in main memory and then only I do the eviction. So how do I basically figure out that whether the block need to be copied in main memory or not? To do that, we will use a flag, and this flag is called dirty bit. Okay. So whenever you update in your cache something, you will set this flag saying that, okay, I have done some update in my cache block only, which is not copied in main memory. And I'll indicate this through this flag called dirty bit. Now, whenever this block need to be evicted, first thing will be checked is whether the dirty bit is set. If the dirty bit is set, that means this block contains some data which is not copied in main memory. So you first copy it in main memory and then you bring the new data. Okay. So this is called write back strategy. Now there are advantages of this write back strategy because many a times we do some intermediate things in our program. Let's say the final value will be something different, but we are updating some variables. Now every time we update those intermediate variables, if we want to update it in main memory access is expensive, slow, So we don't want to do this intermediate updates reflect in main memory. So that's why we can avoid those intermediate updates using write back strategy. And we finally, when we need to update, we do this update once when the block need to be replaced. So this is write back. So this is little complicated to implement, but it is performance wise best because it saves unnecessary writes in memory. So that way it saves power and so on. So whenever you are looking at a performance oriented strategy, then write back will be the strategy which most of the performance oriented uh, uh, basically write strategies will implement. The other strategy is write through. It's simple. It says that whenever you update in your cache, you update it in main memory also. So basically there is always connectivity between your main memory and your cache. Okay. So write through is much simpler to implement, but it basically does unnecessary writes also in main memory. Does this make sense? So we are trying to write something in cache. We have a cache hit. Now, when there is a cache hit, we can either do write through or write back. In write through, whatever we update in cache, that gets reflected into main memory also at the same time. So when we say at the same time, then somebody might ask that then what is the purpose of having cache, right? Because the whole purpose of having cache was I don't want to access the slow big memory. So if we are saying that I'll do the update in cache and then again I'll do the update in main memory also, then how am I saving time? Yes. So basically you don't wait for the update of main memory to happen. You go ahead with the assumption that update in the main memory will happen in the background. The processor is basically going ahead with the updated value which is there in cache. All right. Uh, the other strategy is write back. In write back, we say that okay, we will only update it in cache, and we will have this flag indicating that I have some updates in cache which is not reflected in main memory. So whenever I need to evict that block from cache, I will do the update. Okay. Now, I hope this is fine. So we can move to the next one when there is a cache miss. So let's say I want to write something in memory and there is a cache miss. Now again, I have several choices. So I can directly write it in my main memory because it's not there. The block which I'm looking for is not there in my cache. So should I bring that particular block into my cache and then update? Or I directly go and update in main memory because it's anyway not there in my cache. I have to go to the main memory. So if I directly go to the main memory, then we call this as no write allocate. So I'm not allocating it in my cache. I'm directly going to the main memory and updating it. The other option is write allocate. Now, write allocate says that you fetch that particular block from main memory, bring it to cache, and then update. So there are advantages for write allocate because again, since we have seen that there is a strong temporal locality, that means if you are updating something, it's very likely that you will use the data. So it's anyway you need to bring the data to your cache subsequently. So that's why this write allocate strategy might be uh, more appropriate to exploit spatial temporal locality. But if you are looking at a, let's say, very low footprint processor, so sometime you might use the no write allocate policy. Now, typically the common combinations which are used in most of the processors. So if it is a very simple processor, the strategy will be used like write through and no write allocate. And if it is a performance oriented process, then you will see that it will implement write back with write allocate. Okay. All right. Make sense? Okay. Now, um, just to give you some insight, you have seen that your laptop has cache which has multiple levels, L1, L2, L3, and then it goes to main memory. Okay. Now, between these different levels, uh, you might have different strategy implemented. So, and why so? Because your CPU talks directly to L1 and you want to minimize this access time, the overhead the L1 sees to the minimum. So you can basically the way it is implemented, it almost mimics the kind of extension of your registers. The way you deal with registers, you would like to deal with your L1 memory, L1 cache in the same fashion. So within one cycle, I should be able to access the data, what is there in L1. And this will not be possible if you make your L1 complicated, right? It has to be very, very simple so that it can provide the data which is there in L1 very quickly to CPU. But you need to do lot of housekeeping things in a processor. For example, when you have multi-core processor, each of these cores will have their caches, right? And some cache might be shared. For example, let's say your last level cache will be shared. It could be L3. Now, when you have this multiple cores working on same data, so you need to maintain coherence. For example, if some, let's say core 1 wants to update um, some data block, then it has to let others know that I am updating this particular data block. If you are trying to, if you have a copy of that block in your cache, please invalidate it because I am going to update it. So you will have old stale data. And if you are basically, yeah, so you have to invalidate or you have to let others know to invalidate that data. And whenever they need the data again, they have to copy it again from your last level cache. So this kind of housekeeping, so maintaining this coherence information, right? For example, let's say there are multiple operators who are take any example. Let's say managing admission at IIIT Delhi. Okay, so there are multiple counters. So somebody comes to that one particular counter. One roll number is assigned to that particular person. Now, if the other operator knows this roll number is already assigned, then they will assign the same number to somebody else, right? So that is what happens when you don't maintain coherence. So to maintain coherence, you have to maybe have some strategy that, okay, if this number is taken, then the system knows that the next person should get a new number, not this same number. So maintaining coherence in data is very, very important and it's a very, very critical thing. Now, how do you maintain this? Sorry. So to maintain this coherence, you do have to implement this coherence protocols, which says that, okay, I am going to use this particular block of data, so you invalidate it. Now, if you bring all these complexities in your L1, L1 will become slow. So to avoid that, what you do, you maintain between L1 and L2 write through strategy. So what does that allows? When you have L1 and L2 connected through write through, that means whatever change is happening in L1 gets reflected in L2. Okay, in almost real time. So all the strategies which are complicated, need to be shared with others, etc., are implemented in L2, because L2 has all the updated copies which are there in L1. Okay. And then in the subsequent cache levels, you can have basically write back. So if I have main memory, after that, I can have write back strategy there. So this is just a glimpse that, okay, you might have different stages of your memory might have different strategies implemented for making things work in the best possible way. So this is what is write strategy. Okay. And any quick question before I move ahead? If not, so let's quickly have our class interaction and then we can move ahead. Can you check now? Okay. So we will quickly move to the next one, which is the last aspect of what we wanted to discuss in cache. So any quick question before I move ahead? Okay, so the last thing we will talk about is cache performance and how do we quantify cache performance. So as we have understood that processor request for data, the request goes to cache, and if it is a hit, then the cache responds back from the cache. And if there is the data is not there in cache, then the request is forwarded to main memory. So basically, processor only interacts with the cache. Okay. And then this request is served from the main memory and comes to the cache, and then it is served to the processor. So if you have, let's say, a snippet of code like this, so you have a load followed by some other instruction. So you will see that uh, assuming that there is no problem in the first load, so your data which you are looking for is there in your cache. So it goes through this fetch, decode, execute memory right back without any difficulty, because memory access from cache can be done in one cycle. Okay. Let's say there is a second instruction which is not a load or store, so that goes well, no problem. Now there is another load instruction and there is a cache miss because of it. So fetch, decode, execute. Now, when you reach to the memory stage, you figured out that there is a cache miss. So what will happen? So you will stall in that memory stage, or not stall, basically you will wait for the memory that this load to happen. Now, typically this access to main memory, when there is a cache miss, the access to main memory is orders of magnitude higher delay compared to what you will otherwise have. So in our modern processors, uh, it's almost 1000x, because there are a lot of complexity. We have not discussed about these things. For example, this address which processor is giving is not a physical address, it's a virtual address. So this virtual address need to be translated, and your memory is also divided into pages. So first you have to figure out where this, basically there is something called page table. So you will find out where is your page located, where the physical to virtual mapping is there, or virtual to physical mapping is there. So storing these pages also requires a lot of memory. So basically, where do you put these pages in memory? Is it your cache memory or it's your main memory? So there are a lot of complex things which goes on. We are not going there right now, because to handle those, we have a course on computer architecture. I hope many of you will take it. We will discuss about those things there. We will keep our memory very simple, which gives an address. The address goes as it is. Cache checks it whether the address is there. If not, then it goes to main memory. And when it goes to main memory is slow, so it will take, let's say, orders of magnitude additional time to get that data from main memory. It's not stalled. You are waiting for the memory to be served, right? So let's say this is a load instruction. So you gave the address, the load is still going on. Basically, you could not, the data memory has not given you the value from this load. Now, what happens to the subsequent instruction in that case? It's a pipeline, right? So if somebody is stalled there, because I am waiting for a, let's say, a garma garam roti. The roti is getting cooked now. So once the roti comes, then only I'll move. So everybody else who is standing behind me, they have to wait. No, so 3 is just an example here. So let's assume, huh? So in this example, we showed in a simpler manner that, okay, after 3 additional clock cycles, you will get the data from main memory. Hmm. Huh. Hmm. Hmm. Yes, yes. So whatever time it takes to get the data from main memory. Okay. So that basically slows down your CPI. Every time there is a cache miss, your performance is getting a hit, right? So now to quantify that, we will use this metric called average memory access time. Okay, so every memory access will have basically these two components of time. So every memory access, irrespective of it is a hit or miss, will require this hit time. 100% of your requests will encounter this delay called hit time, because the request goes to your cache. Now, if it is served from the cache, then this is the only delay that particular memory access will incur. Now, if it is not served from cache, basically there is a miss. In that case, the additional delay that access time will take is basically miss rate multiplied by miss penalty. So, so if you want to basically be one way to write it, or we want to explain it in a more simpler way, let's say there are all the memory accesses. I'm considering that the total number of memory accesses is 100%. Now 90% of those memory requests are served by this cache. So in that case, what will happen? So 90%, that means these many requests will have a time delay of hit time only. Now rest of the 10% cases which are miss, what is the time delay they will incur? They will incur the total time delay, which is hit time plus the additional time to access the main memory. Right? So if you now simplify this thing, so you will get the same equation. So here 0.9, here 0.1. So that's how the total all the requests will have hit time as common. Now the next two components. So this is your miss rate. 10% of your requests are getting missed from the cache. So this is your miss rate, and this is called miss penalty. So this is nothing but the basically the main memory access time. Okay. So this is your miss penalty. So using this, you can find out the average memory access time. And we'll keep it simple in this course. We will have only one cache. You might have basically not in your exams, we will not have multiple levels of cache. So you can have multiple levels of cache, and based on that, your at different levels, the access time will be different, the percentages will be different, and so on. But for you, it's only if there is a hit in cache, then it will be served using basically by the hit time. And if there is a miss, then it will take this additional time of main memory access time. Make sense? So we can calculate the average memory access time given all these values. All right. I think in tutorial also we had few questions about memory access, average of memory access time. Okay. Now this is just for completeness. The cache misses can be categorized into three types, and these are called 3 C's of misses. Not very difficult to understand. Compulsory miss. So compulsory miss is that if any memory block has not been referenced earlier, then there is no way you will be able to bring that block in your cache. So the first time a memory block is referenced or requested for, it will be a miss, and that is called compulsory miss, and it is irrespective of how big your cache is. It doesn't matter how big your cache is, because if you know that this particular block need to be accessed or need to be brought into my cache, you will not bring that in your cache, and that will result in a cache miss. So this is called compulsory miss. Capacity miss. Capacity miss, as the name suggests, that the amount of data you are dealing with is more than what your cache can store. In that case, there will be a capacity miss. For example, let's say you are trying to work with a uh, array which requires, let's say, uh, 512 KB of data to store that array. Now your cache size is 10 KB, right? So you, in no way you can bring the all the data which you need in your cache, and because of that there will be a miss, right? And this miss is called capacity miss. So your cache is too small to hold all the data needed by the program, and this will not get affected by replacement policy, because even if you have a very smart replacement policy, your cache is limited, so you can't put all the data. So there will be misses. The last one, which I mentioned earlier also, is called conflict miss, and this is primarily because of the replacement policy or the way you put the data in your cache. So this is misses that occurs because of collision due to less than fully associative cache, right? So if you have two-way set associative cache and then there are three blocks which you are working with, all of them maps to the same set. In that case, you have to evict some blocks and to bring the new data, and that will result in cache misses. These are called conflict misses. So compulsory miss, capacity miss, and conflict miss. So these are the three C's of three types of misses which we deal with. Yeah. Hmm. So you will be given, for example, let's say if you need to go to main memory, it requires 10 additional cycles. Yeah, because you need to get the data to move ahead, right? 10 cycles, yeah. Hmm. Huh. So everything remains same, right? Nothing changes there. So some data just to give you a sense of how you can design your cache and what are the implications of it. So this is again from Hennessy and Peterson book. So it plots the cache size and access time. And also for each of the sizes, there are different implementations. So first one is direct map cache. Second one is two-way set associative. Third one is four-way, and the last one is eight-way set associative cache. Now, if you see the access time and the different ways of cache implementation, uh, you will see that for all the sizes of cache, whether you are looking at 64 KB cache or 512 KB cache, the hit time is best in case of direct map cache, right? So the access time is nothing but the time, hit time for L1 cache, right? So this time is best in case of direct map cache, and this time is basically best in this case, which says that if your cache is small and if it is simple, then you get the best access time. Okay. As your cache becomes bigger and bigger, the access time also increases. And you see that even for direct map 1 MB cache, the access time is almost double compared to a 16 KB direct map cache. All right. So the whole, and you can look at, like, as you increase your associativity, the access time increases slightly. in smaller caches primarily. Okay. So the takeaway from this slide is that to make your cache fast, you need to make them small and simple. Okay. Now, how the access time varies with block size. So the data block, so I can bring lot of data when there is a exchange of block, or I can bring very small amount of data. Remember the block we are bringing in to exploit the spatial locality, right? So here again from the book we have a plot where the block size is in x-axis and the miss rate is on the y-axis and the size of cache is on the other y-axis. So if you have too many blocks or block size is really small, what will happen? Your tag address will be um, uh, basically if you have a large block, your tag address will be small, or you will have limited number of tags to match, because let's say your whole memory is divided into 4 blocks. Now you will have only 4 tags to match, right? Whether there is a cache hit or not. But every time there is a cache miss, you will be moving 1/4 of your memory, basically back and forth. So having big block size has basically this problems that you might also encounter a lot of conflict misses, right? If your data is not very concentrated on a particular block, then what will happen? So you will be going back and forth to move these big blocks, and that will result in lot of wastage of bandwidth. Um, Fewer blocks will have more conflicts. But if your data is bursty in nature, so basically all your data is concentrated on a particular block, then having a bigger block makes sense. But if you look at the impact of block size, so if you have very small blocks, then your miss rate increases relatively. If you have your block size which is, let's say, around 64, then you kind of have an ideal miss rate which is best for irrespective of what kind of cache size you are looking at. So this plot again shows that you should have block sizes which are moderate in size. It should not be too small, it should not be too big. Either way, it will be affecting your performance or miss rate. So last couple of slides. This is cache size on x-axis and miss rate miss rate on the y-axis, and miss rates are plotted for different ways of implementation of caches. For example, one-way or direct map cache, two-way set associative cache, four-way set associative cache, etc. And if you look at the miss rates, typically if you double your cache size, your miss rate usually drops by a factor of √2. So this is again observed through experiments. It's not like something mathematically derived. This is empirical. The other thing to observe here is that um, the miss rate for a 64 KB cache, which is implemented using direct map strategy, is same as a 32 KB cache, which is implemented using two-way set associative cache. So as you increase your associativity, your miss rate improves. So a 64 KB cache, which is direct map, gives you the same miss rate compared to a 32 KB cache with two-way set associative implementation. So basically that means if you have associativity, more associativity, your miss rate gets advantage, little bit of advantage. With small size of cache, you can achieve better performance. Okay. So these are just a few observations, few points I wanted to highlight. I think that pretty much concludes our discussion. Now, if you have any quick question, I can answer. Otherwise, I have something to show you very quickly. Okay, so there is a very nice tool. So if you search Wave RISC-V, you will end up in this website. And if you click, so this is this website. This tablet will not be a very nice screen to put everything. But what I wanted to show is that this is a simulator developed by the Sci5 community. So which actually is the pioneer, which is promoting RISC-V, etc. So in this, you see that you have all the flexibility. So you can select an architecture which is either 32 bit or 64 bit. It has a multiplication unit also. So if I select, let's say, 32 bit processor, I can select whether I want data forwarding or not. So data forwarding activated, deactivated. Then how do you handle branch hazards? So you can have a simple strategy that, okay, I'll flush the instructions which are predicted, let's say mispredicted. In that case, I'll flush those instructions, or I can use the delay slots. So my code will have delay slots, either valid instructions or no ops will be given in the code itself. So all this you can select, then you can load a program. Sorry. So you can load a program. You can type it here. You can copy paste it here. So please do look into it, and then you can do all sorts of, let's say you want to step by step execute this thing. You want to see the pipeline diagram, everything you can see. You can look at the data memory, register contents. Uh, so all these things you can explore using this tool. Okay. So when we ask you to design this simulator and the assembler, one of the purpose was to make sure that you guys can come up with something which will be equivalent of it. Maybe not the GUI. By the way, this GUI is also very, very interesting. You can click on each of these blocks, and so I'll show you how you can basically reach to this. So if you just search Wave RISC-V, you will reach here. And let's say I want to click on any of these blocks. For example, this register file. So while you are executing a particular assembly code, you can see the inputs of this register file, the outputs of this register file. Similarly, all the other blocks. You can look at your ALU. So I think it's a interesting tool to play with. So please feel free. You can get your pipeline diagrams, etc. From this Wave RISC-V tool itself. Okay. So do play with it. I'm sure you will like it, and you can further explore what we have studied in this course. So RV32I, which we have seen, is exactly the same thing. So you have all the instructions, we have everything, so you can really basically do whatever you want to do using this kind of tools. Now, very quickly, uh, we are extensively working in this domain as a group. Please feel free to look up the kind of work we are doing. Some of you have approached and we discussed very briefly. But uh, the design of basically systems is a very, very important aspect. And without that, um, going forward, it will be very difficult to do significant work. For example, any industry you look at, they are aggressively investing on the design aspect of it. So whether it's Qualcomm, Intel, or any other leading companies, even Google, Facebook, all of them are spending a lot of effort in designing their own systems. This course gives you a introductory uh, introduction about how to design our own computers and how our computers actually take instructions and then get the work done. So now you should take up this thing, take up this challenge and build more and more sophisticated systems. And to build those systems, you need to know what is your ALU doing, what is your CPU doing, how you are interacting with memory, where are the bottlenecks, and how you can address those bottlenecks. So we are working on several system on chip design projects. Some of them are dealing with, let's say, accelerating the AI algorithms, uh, running AI algorithms on the edge. Um, uh, even we have some projects which are looking into basically event-driven computation. For example, the computer will not do anything in general, but if it detects an event, then it will start working on things. Um, uh, to solve the memory processor bottleneck, we are working on in-memory compute. Akshay his PhD is on primarily that. Then we talked about basically getting the useful data in your cache. Uh, we only discussed about spatial and temporal locality, but that might not be enough. So you might want to prefetch some data which you know that will be required in future. So how do you design those prefetchers? Now, if you prefetch something and that is not useful, then it will be completely a disaster or wastage of your effort. So you have to be very, very careful about what you prefetch. So again, Akshay is looking into this kind of problems. There are several BTech students also who are working on it. Similarly, we work on approximate computing. We work on secure hardware. Um, as we are building these hardwares, more and more security aspects need to be incorporated. And we do have uh, basically quite a few transaction journals very recently got accepted, which are on security and basically managing the data movement primarily. Um, Many of your seniors are working with us, and basically many of them have got very good industry as well as higher studies options. So do look up, and it's a very exciting field. It was not so 10 years back because everybody thought that architecture is kind of a very, very well studied field, so nothing new can be done. But if you even look at job market, you will see that increasingly industry is looking for people with this kind of system level understanding, because those regular coding, regular verification, or which are let's say not that complicated, those things are taken care by machines. Automation has taken care is taking care of it, and by the time you graduate, I'm sure this will be even more prominent. So you guys need to figure out what is the unique skill set which you bring in, which the companies will not be able to otherwise get done through automation or through other, let's say, students who are not that serious about their studies. So if you are not that serious about your studies, then this is the right time to wake up and make sure that you make best use of your time. do very wonderful projects. IIIT gives you this opportunity to work on several projects. So do make sure that you work on multiple projects with multiple faculties so that you get the hang of it, and then from that you figure out what area you want to pursue further. So all the best for your NSEM. As I mentioned, it's 40%. So even if things are not that good for you, there is lot of scope of improvement. 40% is a huge number. So please do well, and like always, use your concepts. Don't try to memorize. If there is a confusion, write it down that this is my assumption, and based on this, this is how I'm solving it. We will try to incorporate your, if that assumption is logical, we will of course take care of it. Okay. So all the best, and hope to see you soon in some projects or in other courses. Thank you.